now it's everything fine. I'm Andrzej Ptok and I tell you show our results about artificial separation of trivial and topological superconducting domains. And I start from short introduction. Next I show you our numerical result and experimental proposal. And during my presentation I will refer to our recent paper from PERB, and my collaborators David Alspał, Szczepan Głodzik, Axel Kobiełka, Andrzej Oleś, Pascal Simon and Przemysław Piekarz. So I start from very short introduction. Of course, when we speak about topological properties, main source of these properties are spin-orbit coupling, which can be source of many different type of behaviors and properties, like in this very nice diagram. So in our case, most interesting is large bar effect. So as we know, most important or most interesting is realization of Majorana bound state in low-dimensional nanostructures, which is associated with the realization of two zero-energy end modes at the end of nanowires, like in this Coca-Cola with double zero. Typically, we can realize this state at the end of, for example, one-dimensional semiconducting superconductor nanostructure or magnetic monoatomic atomic chain deposited on superconductor surface. However, we can also expect realization of this state at the edge of a two-dimensional system, like in these papers, when we realized in-gap state well localized around edge of two-dimensional square lattice. And indeed, experimentally, we can also expect the realization of this type states, like in this proposal. We have ferromagnetic nano-island deposited on superconducting surface, and around this superconducting surface we expect realization chiral mode, chiral Majorana modes. Additionally, we have also a few additional experimental results. One of them is this nanostructure, where we have semiconducting deposited on this semiconducting bulk system. We have deposited cobaltium nano-island, and everything is covered by superconductor lid. And when we check local density of state along, for example, this nanoflake, we can find this in-gap local density of the in-gap states, which close in some specific point in real space exactly at zero energy. So this crossing along this distance tells us about realization of possible phase transition between topological and trivial phase, and trivial phase in this case is inside in this nanoflake. Second good example of this type system is this experimental result from Hamburg. Probably Professor Wiesendank can tell something more in Monday. Similar here, we have iron monolayer nanoflake deposited on a rhenium superconducting surface, and when we realize STM experiment for energy around zero Fermi energy, we can find a well localized edge state along our iron nanoflake. So in practice, in both cases, we realized some connection between 2 points from the topological phase diagram when we have inhomogeneity in magnetic field, because we connect point A and B. So outside of nanoflake we realize trivial phase, and inside we realized trivial topological phase. So because we have boundary between two phases, topological phases, we expect realization chiral mode around this nanostructure, nanoflakes. So our question is what happened when we have connection between point C and D when we have more or less constant magnetic field. However, we connect points with different chemical potential. So this is very interesting question because we know something from our previous study. This is a result from ultra-cold fermionic gases in optical trap. Optical trap is this red line, and number of particles in this trap is described by blue line, and dependently by shape of this trap we can realize topological phase in whole system or partially only in some parts of them, like here in figure B. So dependently by chemical potential in practice, because our trap is described by this trap, we can realize topological phase locally, and between them we can realize trivial phase. So we can start from very simple model where we have a nanoflake with cylindrical symmetry. We can solve what is interesting. We can solve this model analytically, and we can find realization in this system. Here are mode. This is visible in this AB figure, where we have only one branches inside topological gap. So indeed we expect realization well localized at the edge, some modes, here are modes, and we can also realize real space Bogolubov-Dejean calculation for our system. So this is theoretical lecture, so one slide with equations. We describe our system by relatively simple Hamiltonian. We take square lattice, this part. We assume Rashba spin-orbit coupling. Additionally, we take superconducting order parameter induced by proximity effects, and because we substitute some impurity atoms, this blue one, to our base system in green balls, so we also have additional part Hamiltonian of flake when we change locally chemical potential. So solving Bogolubov-Dejean equation in real space, we can calculate many different physical quantities like local density of state, current, and so on. And now I show our numerical results. So in first step we randomly localized our impurities. We realized nanoflake, and we can introduce by hand some local quantity which does describe some indicator which describe realization of trivial or topological phase in our system. This is a modified relation to this, which describe realization of topological phase in homogeneous system. When we check this quantity, indeed we can find some place, this blue region here, which describe part of system when we expect realization of topological phase. As we can see, red region, this topological phase is surrounded by trivial one, and similarly like previously, we expect realization of Hilbert mode around this nanoflake. So when we check local density of state for in-gap state, this is for example for state nearest Fermi level, we indeed can find well localized edge mode around our nanoflake, and additionally we can also find Hilbert mode. Arrows on this plot denotes direction of this Hilbert mode, and indeed we have mode propagate. Mode propagate around our nanoflake. Additionally, similar like experiment, we can calculate what happened with our density of state when we increase magnetic field. This is very interesting because tell us what happened in our system. So when we can take partially our system as a bulk states. This red region around our nanoflake, blue region, and between them green part, green stripe, we called domain wall. So when we increase magnetic field, we can initially observe close trivial phase, And in some critical magnetic field, we observe open new topological gap, but only in center of our system, in our nanoflake. Now, when we still increase magnetic field, we can find second critical magnetic field, which are connected with bulk states. And what is more, between these two magnetic fields, we still observe in-gap states associated with this domain wall region. So this density of state is similar, have similar behavior like eigenstate of well-known one-dimensional nanowire. Initially, we close our trivial gap, and in some magnetic field we start open topological one. So we observe in our case with nanoflake two topological phase transition, and between these two topological phase transition we can realize artificial phase separation between trivial and topological superconducting domains. However, still we have chiral modes, so we can also ask how we can check chirality of our modes. So we can refer to this very nice physical review letter paper. Authors present results for a P-wave superconductor, and when we connect to this superconductor two leads, ferromagnetic leads, we can check chirality of mode realized in this system. Similarly, in our case, we can realize this two-tip experiment. So we have our system, for example, here in cylindrical shape, and independently by magnetic field, we can realize chiral mode in left or right direction. So when we realized non-local conductivity measurement, we can relatively simply check what direction has our chiral mode. Like here, when one of non-local conductivity has large value, then second one has small. So when we change direction of magnetic field, the direction of chiral mode is changed, and we observe reverse properties of our non-local conductivity. Similar result we can observe in the case local density of state when we check propagation of our mode from first to second tip, and vice versa. So because I haven't time, so I should conclude. So short summary, we study inhomogeneity system when we introduce some inhomogeneity in chemical potential, and in this way we realized artificial separation of trivial and topological superconducting domains. In this system we realized chiral mode, which is observed, for example, in spectrum as a one branches in band structure, and additionally we can check what chirality has our modes. So because this is last lecture in this session, so I thank you for your attention, and I wish you long live and prosper.
Right. Okay. Maybe let's do it this way so that you can have a look at the camera. Now it's my duty to give you this certificate of attendance and presentation of oral invited oral.
Thank you very much.
Okay. Thank you.